In today's course, we will be learning how to use trig substitutions to solve some integrals that would not be able to be evaluated otherwise. For example, this integral. So, for an integral like this, we can see that there's a pattern that's very easily recognizable, which if we look at a right triangle, we can see that if we have a here and b here, this is root a squared plus b squared. Now in this case, let's try making a version of this triangle. So we're gonna put theta here, which you should really put over here in most of your cases, x here, 2 here, and here's going to be root x squared plus 4. So we have x and we have root x squared plus 4, which we need both of them. Now let's erase this example. And let's attain the differential, which is the second step. So if we're going to do any type of substitution, we're going to need to attain a new differential. Now to do this for trig substitutions, you're going to put the x on one side and theta on another side and differentiate both sides. So here is the opposite, here is the adjacent, and here is the hypotenuse. Now for this, it's tangent theta is equal to opposite over adjacent is equal to x over 2, but let's move the 2 to the other side such that 2 tangent theta is equal to x. Now let's derivate both sides. We're going to get 2 secant squared theta d theta is equal to dx. So we have our differential right here. Now let's go to the second step, which is substituting this term. So let's look back at the triangle and we will see that it's hypotenuse over adjacent. What do we have which is hypotenuse over adjacent? Secant. So let's use secant in this case. Let's integrate. Actually no, what am I thinking? It's going to be secant theta 2 secant theta is equal to root x squared plus 4. Now that we have this step, let's square both sides so we get x squared plus 4. We're going to get 4 secant squared theta is equal to x squared plus 4. And in this way, we have not only d theta, but we also have this. So let's rewrite our integral using these two parts. So it's going to be theta 1 over 4 secant squared theta 2 2 secant squared theta d theta. We cancel secant squared with secant squared, 2 with 4, we get 1 over 2, which is going to be integral of 1 over 2 d theta, which is 1 over 2 theta. Let's erase these. It's going to be 1 over 2 theta. Now this isn't the final solution because we want it in terms of x. So what are we going to do? We're going to move the 2 here and we're going to put theta in terms of x. We're going to get tangent theta is equal to x over 2, and theta is equal to tangent inverse, or in this case, you're going to have to learn this type of notation and use it more frequently, arctangent of x over 2. So it's going to be 1 over 2 arctangent x over 2 as the final solution of this integral. Now, what's the most applicable case of this? Let's say you're trying to find the area under a circle of any dimensions. This is useful for the equation of a circle, which in this case is x squared plus y squared is equal to r squared. Or in this case, it's a full circle and it's not a function. You have to move it to the other side and then you get a function. But in this case, we can use this rule to integrate a function that we otherwise would not be able to do so.